Hello, I'm Sophie Rovner from the American Chemical Society. Welcome to this news briefing from the ACS Fall 2020 virtual meeting and expo. We're joined today by Dr. David Martin from the University of Delaware. He's studying cyborg technology that could enable new diagnostics and the merger of humans and AI. Dr. Martin.
Hi, thank you so much for giving me this opportunity to talk about our work. So we've been looking at polymers that are both electrically and ionically conductive. And as was mentioned, one of the areas where these materials are really interesting at the moment is for interfacing a whole wide variety of different electronic biomedical devices with living tissues of various sorts. So examples of these might include pacemakers that go in the heart, or deep brain stimulators that go into the brain for treating Parkinson's disease, or cochlear implants for the ear. But there are also a number of other devices that are being considered, such as peripheral nerve interfaces for restoring motion or interfacing arms and legs with bionic components, or even electrodes that would be someday implanted directly in the brain and would be used for long-term brain-machine interfacing. So the polymer that we've been looking at is a functionalized polythiophene known as PDOT. PDOT is available commercially and is sold as a suspension in a bottle. We have been looking at chemical variations of PDOT that allow us to more specifically tailor its properties. So conjugated polymers like PDOT are important for this application because devices are hard, rigid, metallic or semiconducting, crystalline, inorganic compounds, whereas living tissue is a soft, squishy, wet, ionically conductive substance. And conjugated polymers are able to talk to both sides of this interface. So they have structures, mechanical properties, and specifically tailorable chemistry that allow us to create new materials that can better integrate into the tissue that we're trying to connect to, as well as improve the adhesion and the mechanical properties of these films on the devices themselves. So next slide. So this is a quick snapshot of the deposition of one of these polymers onto a particular type of device. Shown in the upper left is a microfabricated electrode that was designed at the University of Michigan, where they have a center for neural communication technology. And there are, in this case, 5 metallic electrodes, about 40 microns in diameter. And to give you a sense of scale, that electrode itself is about 150 microns. That's about the width of a human hair. So you're looking at 5 little electrodes, and we've coated 4 of those electrodes with more and more conjugated polymer. So the polymer is very dark black, and as you put more and more of the polymer onto the electrode, it gets sort of fuzzier and hairier. So in the upper right-hand corner, you can see scanning electron micrographs of these coatings as they get thicker and thicker. And you can see just from looking at it that what's happening is we're creating a film that's got a lot of effective surface area. And so the performance of these devices is really critically tied to this increase in the overall amount of surface area that can interface from the metallic electrode at the bottom to the ionically conducting tissue that we're trying to communicate with. So we examine the electrical properties of these devices using impedance spectroscopy. An impedance spectra is shown in the lower left. And the important frequencies that are used for biomedical devices are everything from 1,000 hertz or 1 kilohertz and below. And if you look at the electrical properties in that range, they drop dramatically. So in the lower right, you can see this graph of the impedance dropping by 100, sometimes 1,000 orders of magnitude when we deposit these coatings on the electrode. Now, the reason that's so important is that impedance controls the energy requirements, meaning the battery lifetimes, the sensitivity, the voltages, the safe operating window that you can use. So many, many properties of biomedical devices are critically related to lowering the impedance. And in fact, if you want a really tiny electrode, which is what you want if you want the more precise local ability to talk to or listen to cells in the body, the very small electrodes have always been very difficult to manufacture because if they're flat metal electrodes, they always have a very high impedance. And so this technology provides a way of making very low impedance, very tiny electrodes that can significantly improve the precision and performance of these devices. Next slide. So what's new? So PDOT itself has been around for quite some time. But what's new from our laboratory is that we now have a whole library of new PDOT molecules that have different side groups. So we've made a PDOT aldehyde, a PDOT acid, which is actually a molecule we've studied for quite some time. And more recently, biologically functionalized molecules like the PDOT dopamide and the PDOT tyramine. Dopamide is a neurotransmitter molecule found in the brain. Tyramine is a amino acid that also has important biological properties. So we're making now PDOTs that have biomolecules all along their backbone. And in particular, of particular interest to us is the PDOT maleimide that's shown on the left in the bottom row. That maleimide moiety is extremely functional and useful for creating a whole wide variety. So there are many, many different reactions that can be used now that we've created PDOT maleimide that we will be studying in the future. And so that's what my lab is up to right now, evaluating the performance, long-term behavior, and properties of these materials. So that's a quick overview of the science and the motivation behind it. And I'd be more than happy to answer specific questions that might come up.
All right, thank you. So at this point, I would like to invite questions from viewers. Please state your name and affiliation in the chat window when you type in your question. I'll get us started with a few. So how did you get the idea to do this project?
Well, when I started as an assistant professor at the University of Michigan, my sister was actually working in the Kresge Hearing Research Lab, where they had been working on electrodes to be inserted into either the ear or the brain. So this is something that had been going on at Michigan for quite some time. And so I learned about the technology and what the current issues were. At the time, I was actually very interested in genetically engineered proteins that could promote specific interactions with cells. Professor Dave Terrell had started this work when he was still at the University of Massachusetts. And I was in graduate school at UMass in polymer science and was fascinated by those materials and was working with a small company that had actually tried to commercialize those. We started looking at whether they might be useful for these biomedical device applications. And then I'd also been doing a lot of work with these conjugated polymers, doing fundamental studies of structure. And it became clear that what was really important was improving the electrical properties, but still retaining some of this biofunctionality. So it goes back a long time and has to do with just people that I knew and people that told me about problems that they were interested in. I just kind of looked at what the limitations were. But I've always been very interested in materials that interface engineered devices with biological systems. I mean, I read science fiction like many other scientists, and there's lots of examples from movies, you know, where you have Luke Skywalker or, you know, the $6 Million Man, where people are trying to interface electronic components. And in the biomaterials field, frankly, there's been a lot of work to make non-electrically active biomaterials that, you know, artificial hips or artificial eyes or things that were more mechanically inclined. But I didn't see very much attention being given to electrically active materials, even though there's a lot of electrically active tissues and a lot of electrically active things that these kinds of materials would be able to do. And it's frankly only been recently that we've been able to make electrically active polymers that are so chemically stable, like these materials are, that we can even consider putting them in the body. The first conjugated polymers that came out were only stable if they were kept at low temperature inside a glove box away from oxygen. And so it's remarkable. Actually, that's the real secret here, is that we have found materials that, in hindsight, it's not so surprising because they're actually similar in chemistry to other naturally occurring conjugated polymers like melanin, the molecule that's in hair and skin that gives skin and hair color. So those tissues are dark because they have a lot of melanin in them. That's from the conjugated molecules that are in hair. When you bleach your hair, you're oxidizing the melanin. So there's a lot of interesting things just to learn from looking at natural systems and trying to build this bridge. So anyway, it's been a long-term intellectual focus of mine, and just really happy to see that we're getting very close to actually having these materials start to really help people out. That's been very satisfying.
So why might somebody need or want an implant in their brain? What would that be used for?
Well, let me give you perhaps the most dramatic example, and that is in Parkinson's disease. So a person with Parkinson's disease may have tremor to the point where they really are not able to even function in a basic sense. So a person with severe Parkinson's disease is not even able to feed themselves or to do other ordinary tasks. And if you look at the before and after of a person who has a deep brain stimulator that's put into the right part of the brain that can suppress the symptoms of Parkinson's disease, a person with a brain stimulator with Parkinson's, it's almost not possible to tell they're even ill. Like, it is almost that they have been completely restored to normal function. Sometimes you might hear a little bit of a slur in their speech because the electrodes sometimes are close to the speech processing centers in the brain. But all you have to do is go to YouTube and type Parkinson's deep brain stimulator. And once you see these videos of before and after, the change in the quality of life for a person with severe Parkinson's is just absolutely incredible. But there are so many other examples: pacemakers, cochlear implants, retinal implants, where people are now able to see again with electrodes in the back of their eye, able to hear again with electrodes in their ear, able to have some kind of a prosthetic device that can move. So we're very close to having, very precise prosthetic arms. So one of my colleagues back at Michigan is actually doing what's called an RPNI, where he wraps around the end of a severed peripheral nerve for a person who's an amputee a little device that's got a piece of muscle in it that helps the nerve regenerate back into the muscle. And then with some electrodes and wireless connections, you can imagine having tens, hundreds, maybe even thousands of interfaces where you could have a truly articulated arm that could even not just do things, but sense things. It would send information back. And so, the future, I think, is very bright, and there will be a lot of these technologies. My own little piece of it is to try and enable these devices. It's possible to imagine the different components, but what we're really talking about is the problems that are right at the interface between the device and the tissue we're trying to talk to. And we're trying to make that efficient, stable, and safe. In particular, it's got to be very safe. We don't want to be doing anything that's going to cause, any long-term damage or issues. So it's got to be done cautiously and carefully, and just be absolutely sure that, we're not causing anything that might lead to any problems down the road. So it's good to be excited, but you also have to be very careful because we're talking about the quality of life for people here.
And the press release also mentions the issue of scarring. So what causes that with implants, and why might PDOT prevent that scarring?
Yeah, that's actually a very common thing. Whenever you put an artificial material, or even when you get a splinter in your hand, your body is programmed to scar around the device or around whatever the foreign object is there, because it's trying to protect itself. So let's imagine an electrode going into your brain, for example. Now, luckily for us as humans, we don't often have hard wire objects inserted into our brains. So the brain is actually not as active a tissue as, say, if you were to get a splinter in your hand, there would be a very robust reactive response. So the brain is a little, but there still is a scar, if you like, a scar that will form in the brain. And the problem for a very sensitive small electrode is that if any kind of scar forms around that device, the electrode, the teeny tiny electrode that's trying to talk to individual neurons, can no longer hear or talk to the cells that it's trying to communicate with. So even a tiny amount of scar is very problematic. So in the past, there have been a number of strategies to try and create, say, attractive molecules on the coating to get the neurons to try to grow through the scar to get closer to the electrode. But in fact, that's kind of, we think, not the best approach. We've been looking at a different approach where you can actually grow the polymer electrically through the scar. So what you do is you stick the electrode in, and you can either do the polymerization right away or let it wait for a while. And then you can actually electrochemically grow the polymer across the scar and then communicate locally with the tissue by making a locally electrically conductive scar, or making these kind of long tendrils of electrically active polymer that we hope will be able to be even less reactive or deal with the scar. So you can actually get the advantage of the scar. The scar stabilizes the electrode. It prevents the blood from getting out. So when you stick a needle into the brain, you're always going to rupture a few blood vessels. That's not good. So the scar actually helps to protect and seal off the brain from the wire. But now what we're trying to do is to try and grow the polymer, the electrically active polymer, sort of molecular wires, if you like, across the scar to talk to the tissue. And we have made progress. So we have made a couple of papers showing that the approach is feasible. And we've done it in the hippocampus of rats, and the rats are still able to remember what they are supposed to do. But we just need more time and money, frankly, to investigate the details of this. And these new materials we've been developing, we hope will be more important for that, because the PDOT wasn't really designed to be cyto-friendly. It was designed more as an organic electronic coating. But these new monomers that I described in my little presentation there are much more cyto-friendly. They're much more able to be accommodated by the tissue. So we are more optimistic that they will be able to be used in the future. But to be frank, we still have a way to go to convince people that this all makes sense, and we want to, we have to go cautiously but aggressively. So, and again, I'm now an administrator, so I have less bandwidth to focus on stuff. But you just do what you can.
Yes. So it's an interesting blend of caution and aggression there.
Yeah, well, your exactly. You have to think out of the side of the box, but then you also have to be very, cognizant of the fact that we're talking about, sticking wires and things into human beings. So we don't want to be doing anything until we know that actually is a really good idea. And yeah, I'll admit, I'm not yet convinced it's a really great idea. I think it's a good idea, but even if it just teaches us something about the dynamics of transport near the device, or something about, when we watch the polymerization, for example, you can see that it follows certain structures in the tissue. So you can think of it even as a dye or a stain, if you like, for the local environment around the probe. And so, maybe that's the angle we should be investigating more aggressively first. And if it ever turns into a therapy at some point, then that would be a best outcome. But just the science itself is still worth doing, I think, But. And
so you're indicating some caution there. What is your concern? Why might it not be a good idea?
Well, you just, so whenever you stick let's say, and whenever you have something inserted into tissue, it's probably inevitable that some of the cells right near the device are going to be disrupted, and there has to be a little healing that has to go on. So like, for example, if you get an artificial knee or an artificial, even a tooth implant, right? There has to be a little bit of drilling to get the tooth ready to accept the implant that you're putting in. So some cells have to give up their lives for the greater good, if you like. It's kind of a battle, but you want to win the war. But there are going to be a few soldiers near the place of the implant that are going to have to either remodel the tissue, but the tissue can often accommodate that and heal, and there's no long-term issue. It's like getting surgery. There has to be a cut, right? So you can't have surgery if there isn't a slice of a scalpel. Then some skin is giving up itself for the greater good. If you know, getting a nose job or whatever, you have to do a little cutting. So you have to break bread. You know, if you're going to make bread, you got to grind some wheat. So the whole question, though, in terms of added value is the damage or the problem that you create by putting the device there, are the benefits, do they outweigh, you know, the issues that might be happening there? So you can't plow a field if you don't break the ground. I mean, there's all kinds of analogies, right? So, but you have to be careful, you know, because you are going to be cutting things. You don't want to cut, you don't want to kill a cell if you don't have to. But, you know, if you have to, then you have to, and you have to figure out if you're trying to save the person, you know, that's the more important. So, you know, it's just a question of evaluating and understanding. And when the technology is new, all these questions are still up in the air, but they have to be evaluated carefully and critically and cautiously. So I understand that, and I'm happy to work with, you know, I'll tell you, the problems quickly get to be so big that a little investigator like me at a university with a small research lab has no hope of getting the numbers fast enough to really understand all of the different issues, which is why I've been very interested in trying to work with companies that have spun this off. So when we were still at Michigan, we had a small company that spun the technology off and worked on it for about 10 years until it was fully acquired in 2017 by a German company, Heraeus Medical. So, but again, that only happened because I had students and postdocs who were themselves willing to do the heavy lifting of making it really happen, you know, working with the tech transfer office and securing the IP and everything. So, and I only have so many hours in the day, and trying to teach class and run my lab and say hi to my family once in a while. You know, these are the go to sleep, eat, you know, these are the other things that, you know, I don't want to look back at my kids and introduce myself to them when they're grown
like,
and have their own kids, right?
Who is that?
Yeah,
and
who are you?
Are you still working with that company?
Well, yeah, well, the company, Heraeus, the company we spun off was called Biotectics, and the big German company is called Heraeus Medical. They are part of the company that developed platinum back in the 1800s in Germany, techniques for making platinum. And so now they have this as part of their portfolio, but they acquired the technology from Biotectics, and it's now kind of behind the firewall, and I'm not engaged with them in any way at the moment. I mean, I don't know if they're listening, but I'm happy to, you know. But we have the newer molecules, you know, the University of Delaware now has certain patents that have been issued and others in process that, you know, the patents are owned by the institutions. And so there are people at the institutions that make the final decisions about what's the appropriate thing to do with technology that a university develops. So I'm more interested in the science, and if something comes out, I'm great if it helps people, but that's, you know, I'm an engineer, so I love to see things that help people, but I can't predict it, and there's only so much I can do as an individual to help it.
All right, so just let me see what other questions are here. I think we've covered just about what we need to. What would you say is the message you would like viewers to take away with them?
Uh, well, that there are interesting polymer materials that act like little electrically conductive wires and ionically conducting tubes, if you like, that can be functionalized to have coatings that are useful for integrating all these different technologies for the future generations of, assistive devices, if you like. I mean, I had somebody, I think you guys used the word cyborg in the title. I mean, I don't know, to me, I had a reporter from the Daily Telegraph ask me this question yesterday. He's like, what do you think about the word cyborg? And I was like, well, I don't mean, to me, cyborg is a word that kind of has this bad or evil kind of, like it's some kind of robot man machine complex or something. All we're really talking about is technology that we can integrate better into a person so that it can assist them in what it is they're trying to do. So, people have been using technology for long periods of time. We wear shoes, we use canes perhaps if we're older. So what we're really trying to do is to give people who can't do a certain thing some measure of the function that they've lost, to give that back to them. So and we want to do that in a safe and efficient manner, and hopefully, I don't know how long it's going to take. It's fascinating to watch the technology move, and like I said, I watch movies and I see all this stuff happening, and I'm just, hopeful in 50 years, maybe somebody will pull up this interview or some other talks that we've done, and, maybe the technology will have gone in a different direction, but I think at least it helps you look out into the future. I've heard it said that the future is hard to predict because it hasn't happened yet. But hopefully by looking at the trajectories or the slopes, it'll be possible to get a glimpse of what's coming. And hopefully, the work that my students and colleagues have done will be, remembered in the long term for good. We want it to be used for, helping.
Absolutely. All right. Well, thank you very much. The archived version of this session will soon be posted at www.acs.org/fall 2020 press conferences. Please join us for our next press conference at 1 p.m. today on targeting iron uptake to create a new class of antibiotics against UTIs. Thank you.